Hello class. So in this video, we're going to finish example 1, section 6.5. I was doing it in the last video, but then it got a little bit too long, so I decided to just cut the video and then do this in a different video. I do want to show you how to do this because so you can have another example of how to actually calculate a Laplace inverse, and also because it uses the Laplace transform of functions that we haven't seen yet. So I'm going to give you what those functions are, and then with that, we should be able to calculate the Laplace inverse of this. Okay. So first, let's write the functions or the Laplace transforms of functions that we're going to need. So we're going to need that the Laplace transform of, let's see, e times at times, so that's all in the exponent. Looks like this is coming off. Yeah, so this product, right, so we really haven't seen at the Laplace transform of a lot of products. Like we've seen something like this in the case that, so let me show you the theorem. So this is the theorem. Where is it? Yeah, so we've seen something like this, right? So really, it's just an extension of this theorem here, right? Where if you have e to the ct times a function f of t, well, what's the Laplace transform of that? Well, it's just the Laplace transform of just the function c, f of t, sorry, but shifted c units to the right. Okay? So let's go back to this slide here. So because of that, right, we know what the Laplace transform of sine of bt is. Right? We could see it in our other theorem. So it would be b over s squared plus b squared. So in our case, b is k. And then we shift that a units to the right by theorem 2 in section 6.3. So if we do that, we get b over, so a units to the right, s minus a squared plus b squared. Then this is for s greater than a. So we're going to need that one. And then we're also going to need the one for cosine. So again, this is all coming from theorem 2. Here I'm just giving you the formula. But again, all we're doing is applying theorem 2 here. If you have an exponential, there's f of t. It's just the Laplace transform of that. It's just the Laplace transform of the original function, shifted c units to the right when c is the exponent of the function e to the ct. Right? So whatever the exponential has, that's the exponent there. That's how much you're shifting the function. So let's go back. Okay, so here we're also going to need the Laplace transform of e to the at times cosine of bt. And this is going to be s minus a, right? Because it's s over s squared plus b squared, and then we're shifting everything a units to the right. So s minus a squared plus b squared, again for s greater than a. So again, this just comes from theorem 2, from section 6.3. We're going to need these. Why? Because, well, first I'm going to have to rewrite this big X of s. Right, so I'm going to write it as, just using the linearity. Well, not the linearity yet, but just separating the fractions. I'm going to separate it in a clever way. And I'm also going to write s squared plus 2s plus 2 in a clever way. I'm going to write it as s plus 1 squared plus 1. Right? And you can do this by just completing the square. Right? So it's something that you should have learned in college algebra. So if you complete the square on s squared plus 2s plus 2, you get s plus 1 squared plus 1. Now here, I have an s plus 2 on the numerator. I'm actually going to separate it as s plus 1 over s plus 1 squared plus 1. And then I have a leftover 1. I just want to write that here. Okay. Now, I'm going to take the Laplace inverse of all of these. So x of t is going to be the Laplace inverse of x of s, big X of s. I'll make that a little bit bigger. Which is going to be equal to, by linearity, the Laplace inverse of this first term. Let's just give them names. Let's call them 1, 2, and 3. Okay, so it's not that much writing. So the Laplace inverse of 1, the term, not the function 1, plus the Laplace inverse, oops, it's weird, L. The Laplace inverse of expression 2, plus the Laplace inverse of expression 3. And we're basically going to tackle each one separately. So let's go ahead. Let's start with the Laplace inverse of expression 1. Let's do that in blue. So the Laplace inverse of expression 1, it's e to the negative pi s times 1 over s plus 1 squared plus 1. Now, I write it like this for a reason. Like I did this in an example in the previous videos in section 6.4 or 6.2. I'm not exactly sure, but in one of those sections, we did something like this, where basically what we want to use is use, where is it? I think theorem 1 in section 6.3. Yeah, we want to use this underlined in red. Right? The Laplace inverse of e to the negative cs times the Laplace transform of a big function of little f, which is big F of s, is equal to u sub c of t, or it's this unit step function, times f of little f of t minus c. Right? So it's kind of hard to read, so I'm showing it to you here. So we've used this one before, and we're going to use it here again. So basically what's going to happen is, and as we saw in the other example we did, we know that from this exponential, right, we're going to get something that looks like u of, right, c is pi in this case, so u of c of t, times f of t minus pi. Right? And what's this function f? Well, this is a function f that satisfies that the Laplace transform of f equals 1 over s plus 1 squared plus 1. Again, this is by theorem 1 in section 6.3. So we just need to find a function whose Laplace transform is 1 over s plus 1 squared plus 1. Right? So it's either going to be e to the at times sine of bt or e to the at times cosine of bt. Now this fits precisely or exactly the form for e to the at times sine of bt, right? Where a is negative 1, right? So we get an s plus 1 squared here. Right? And then b is 1. Right? So if b is 1, we get 1 squared over 1, and 1 in the numerator. Right? So that is exactly 1 over s plus 1 squared plus 1. Right? So what's the function who satisfies that the Laplace transform of it is this expression? Well, like I said, it's precisely this e to the, okay, let's see. So a is negative 1. So just e to the t. So negative 1 times minus t is positive t. All right, and then let me double check the formula. Sorry, the formula that I wrote here, just to make sure. Yeah, so minus a, oh, so if you're subtracting a, so negative 1, so it's actually negative t. Yeah, so whatever a is, sorry, so it should be negative t. It's a good thing that I double checked the formula. And that's, you can verify, a is negative 1, yep, okay. And then b is 1. So here we get a sine of just bt, but b is 1, so just t. Okay. Right, so then what's this Laplace inverse then? We plug everything together. It's going to be equal to, so this part, u sub pi of t, and then f shifted pi units to the right. Okay. Our f is this, so we just shift everything pi units to the right. So e to the negative t minus pi sine of t minus pi. That takes care of the first term. Now the second term is going to be similar. We just don't have the exponential, so it's a little bit easier. Okay, so now we're trying to look for the Laplace inverse of s plus 1 over s plus 1 squared plus 1. So now this is again going to be either a sine or cosine. So let's go back here. Now this looks a lot like the cosine one, right? The e to the at times cosine bt, right? Because a would be negative 1. So we would have s plus 1 in the numerator, s plus 1 in the denominator, and b is 1, so we would have the plus 1 squared. Right? So it precisely matches that formula. Right? So it matches, again, when a is negative 1 and b is 1. Right? So we get e to the negative t times cosine of t. Again, because b is 1, a is negative 1. Okay, so that one's pretty simple. Then finally, the last one, we're looking for, now let me change colors so it looks a little bit less monotonous. Looking for the Laplace inverse of just 1 over s plus 1 squared plus 1. What is this going to be? Well, again, now we don't want to use the cosine version because we have an s there. And remember, with s's, we can't really move them out. So we actually have to use, oh, we already found this, right? Wait, we already found this. Yeah, we found it here for the expression 1. It's just e to the negative t sine t. Yes, I don't have to explain anything. So we already found this. Okay. And that's all. That's the 3 terms. Right? So just add all of them. So that's x of t. So the first term was u sub pi of t times e to the negative t minus pi sine of t minus pi plus e to the negative t cosine t. Right? This was the second term. Plus the third term, e to the negative t sine t. And that's the answer. So again, a little bit of work. And again, the work came in, well, using these two, finding what these Laplace transforms are. Right? This was by using theorem, what is the theorem? Yeah, so theorem 1, section 6.3. Oh, no, sorry. Theorem 2. Yeah, theorem 2. Right, so this was by using theorem 2, section 6.3. Right? So that's how we got those formulas. And then we rewrote our expression. So remember, initially our expression, big X of S, just looked like this. Right? So we had to do a little bit of work. We rewrote the denominator as by completing the square into x plus 1 squared plus 1. And then we separated the numerator in a way such that everything matches something that looks like either sine or cosine, or the Laplace transform of e to the at times sine of bt, or the Laplace transform of e to the at times cosine bt. Now, there's a lot of work in a problem like this, so I won't ask you to do something where you have to rewrite and be clever in this way, like too much work. Like I won't ask you to complete the square or anything like that. So this is a little bit hard compared to what I would ask you in the exam. So definitely won't ask you to complete the square. But if I gave you something, your x of s already in this form, like I gave you in this line, then I could ask you to find the Laplace inverse of this, right? Again, and I would have to give you what, these two transformations, or ask you to find what they are using theorem 2 in section 6.3, right? Either way. Okay. So hopefully that's enough examples of taking Laplace transforms and taking Laplace inverse, and in general of just finding the solution to initial value problem using the Laplace transform. Okay, so that's it. I'm just doing one example in this section. I mostly just wanted to introduce the Dirac delta function, which we introduced in the previous videos, and show you another example of calculating the Laplace transform, where we use specifically a Dirac delta function. So in the next video, we're going to cover section 6.6. We're going to be talking about convolution of functions and the convolution integral.